Okay, so you're playing a game. You're trying to make the best possible choice. Trying to choose the best actions. It's a little bit like choosing the best policy. How are we going to do that? How do we decide between A1 and A2? And people said, all right, compare the values of the Q function and choose whichever is larger. So let's look at the note that we were writing. And we had this Q function. Let's see if the definition of the Q function is somewhere here. Yeah, another type of value function. So here are the two definitions of the value function V and the Q function Q. The value function is the average of the total return you get for some policy pi. If somebody tells you what the policy pi is, then there's no choosing the policy. You just have the value function under that policy. That is what you're doing on your homework. So homework 2, I give you the policy, and I ask you to compute a bunch of different V's this way. And that is all the stuff we did before we learned about actions in the first place, was actually doing this V sub pi. We just didn't write pi. And that was because this observation, once pi is fixed, you take all the decisions out of it, and a Markov decision process with making choices becomes a Markov reward process, just like observing the game and seeing what rewards you get. So that was like snakes and ladders or something. So that was V, and V is the total return. Maybe it's worth writing down what the total return is. The total return, remember, is the sum of all rewards. The sum of all rewards. So a reward is what you get like once, and maybe you can like step on something. You have this chain of rewards. Maybe you get a whole bunch of rewards over and over again. But the total return is the sum. So in the book they call this G, and they say G sub 0 is the sum from t equals 1 to infinity of RT. And if you are putting a gamma in there, a gamma discount factor, you multiply by gamma to the power t to discount the future rewards. So this is the total return. The value function tells you from the starting state S, continuing on into the future, how much return will we get on average. That's the value function V. Okay, in contrast to that, the Q function Q, very similar, except for there is one extra thing, which is the action. So you have this action A. And instead of just following the policy forever, we do this action A first. So we first pick action A, and then we go forever and ever. So that's the Q function. I think it stands for quality. It tells you the quality of the different actions. And we had this equation last time that we were deriving. I will go over it in more detail. Again, we had two sort of equations that were interrelating Q and V. So V pi star is the maximum over the Q pi star, and Q pi star is something involving V pi star. So that's very nice. So there you go. Q involves actions, and V involves value. Any questions or comments so far? It's all sort of review. Okay. Why am I bringing all this up? Why is it important to review? Because this answer that 13 people chose is the wrong answer. So 13 out of 16 people got it wrong. This one is wrong. I will let you revote now that I've explained the review. This one is wrong. There's something important that you guys missed. If you picked this Q thing, you are missing an important detail. So let me let you guys revote between the last two options, and we'll see what you guys come up with. So let's do it one more time. Duplicate this thing and present. And I want Q versus V, V2. So it is not this one. It does not compare the values of the Q function and choose whichever is larger. I'll let you think for another minute. Okay. Okay, it's been 1 minute. So new votes are in, and let's see what people said this time. All right, this time we have 13 people in you can't figure this out, and 3 people say it's comparing values of the v function, and the answer is you cannot figure this out without a policy. So very good, you figured it out. And I would try to be a little bit deliberately tricky over here by leaving something off of the q. So what did I sort of, I just said the q function, I didn't write the full notation. What was I forgetting? Yeah. That's right, so both q and v depend on the policy pi, right? So if you are doing one particular strategy, maybe some states are good and some states are bad for that, so the v function can be different, right? So if you are looking at the value function, how much will we get on average? Well, it depends what choices you're gonna make, right? So example, in the dice game Pig, maybe you're choosing a very greedy strategy and you're just gonna like keep re-rolling over and over again until you get to 100 points in one go. Then, those are some bad choices. You're gonna have a very low value function. If you're, on the other hand, are doing the thing that we found last time, which is let's stop at 20, we're gonna roll below 20, and if we're above 20, we'll stop, then your v function will be very large. So by changing the policy, you can change the value function v. It depends on the policy. And similarly, the q function also depends on the policy. The q function is basically the v function, but with one choice made for you. So if you're gonna make all sorts of bad decisions in the future, then the q function can be higher or lower. And if you're gonna make all sorts of bad decisions in the future, maybe it changes which one is the optimal action A. So you can imagine like, if you're trying to decide, am I gonna roll again or stop at this number? To answer that question, you need to know what's going to happen if you like succeed, or what's gonna happen if you roll a 2. So like last class we said roll again if you're less than or equal to 20 is a good strategy. But that sort of like depends on consistently following the strategy. Like maybe you're like, if I ever get to 21, I'm just gonna go crazy and like roll the dice forever. Then you wouldn't want to re-roll if you're like 19, right? You want to avoid the crazy situation. So it's really important that you remember that this q function depends on the policy pi. Without that, it doesn't make any sense. So it's tempting to think it sort of tells you how good everything is, but it only tells you how good things are in the context of some particular policy. All right, that was the point I was trying to make with this warm-up question. I think this is a great place to stop. We got these two actors, Q and V, and in this class we're going to see how they combine together to let us sort of solve things. Any questions or comments at this point about Q or V or how they interact? Okay, so here is the big conundrum, right? If Q depends on the policy and you're trying to find the optimal actions, right? You might think, oh, let's maximize Q, right? Or like choose the action that has the higher Q value. But that depends on the policy pi. Okay, but if I'm trying to find the policy pi, now I have a chicken and an egg problem, right? To find the best action, I need to know the policy. To find the policy, I need to know the actions. Like, how do I solve it? And it's exactly the same situation as we did before. We're gonna find an equation that the optimal policy satisfies, and then we're gonna just iterate that equation to try to solve it. So just like cosine of x equals x is an equation that the thing we're trying to solve for satisfies, and then we iterate it to solve. So that's what we're gonna do. And that is the so-called Bellman equation. So let's do a little recap of that before, down here as well. So a few classes ago, we had the so-called baby Bellman equation. Baby is my name. I don't know what other people call this equation, but it's essentially the equation for just the value function on its own, and it says, so for fixed policy pi, or AKA a Markov reward process with no choices to be made. And in this situation, it just tells you what v pi is in terms of itself. So the value function pi equals the reward vector. I guess that also depends on pi. Does it depend on pi? Yeah, I guess it does. Okay. Plus m, and m depends on pi, v pi. So what are these things? I'm going to write them as vectors. I mean, really, they are functions. V pi of s is the value function, the long-term total returns, the total return from, I'll just say total return, and then I will write given given s is 0 equals s. I'll say under pi, so with the policy pi in mind, r sub pi of s is the reward you get now. So the expected value of the reward now. So in other words, the one step reward, that's what we called r. So r1 given s is 0 equals s. So you start at the position s, and again, you're following pi, right? So maybe if pi is a good policy, this reward will be good. Otherwise, maybe it'll be bad. And last but not least, m, I'll say to the power pi, is the probability matrix. The probability to go from s1 equals s prime, from state s to s prime, under policy pi. And all of these things depend on pi. Pi is like what choices you make, and that affects where you go. And so we had this equation before, but we didn't write the pi's. The pi was like understood as being part of the chain. Now we're thinking the chain depends on the policy pi, so we got to write pi's everywhere. This was the so-called baby Bellman equation, and in fact, that's what you'll be using in assignment 2, because I've told you the policy pi. Any questions or comments about this equation and how it works? And once again, like the reason you can think of it as a function or as a vector, the reason we think of it as a vector is so we can do this matrix vector multiplication. If you don't think of it as a vector and a matrix, then you have to write down this operation of doing the linear combination of values of the function, and it's kind of annoying. But if we write it as a vector matrix, then it's the vector matrix product, and that's why linear algebra class is the way it is. Okay, so that's the baby Bellman equation. And last class, I sort of gave the derivation for the real Bellman equation. So this is the Bellman equation for pi star, right? So this is, you tell me the policy, and I can figure out the value function. In the Bellman equation for pi star, it not only tells you what is going on for some policy pi, but it will tell you the optimal policy pi star also satisfies some particular thing, and we are going to solve it. And again, it is a bit of a chicken and an egg problem. So one thing the optimal policy satisfies is that the value function, the optimal value function at some state s, is the maximum of all of the actions that you can take from state s of the q function, q pi star, of s comma a. So if you're playing optimally, then at every situation, you are doing the optimal thing depending on q star. So the optimal policy satisfies this. Non-optimal policies maybe have some states where they choose a suboptimal action, but the optimal action, or the optimal policy always chooses the optimal action. Maybe that's what it is. I'll write it like this. The optimal policy always chooses the optimal action. Okay, and if you were confused about what these things were, then you might think, okay, we're done. Like, well, you just write this down, and then you take the maximum, and then you're done. But as we saw in the warm-up problem, the real issue is that q also depends on pi star. So if you're trying to figure out pi star, you don't know what's on this side, and you don't know what's on this side. But you can come up with another equation. And the other equation that we came up with is this one. It's q pi star of s comma a. What is it? Well, you can divide it up into two parts. There's the rewards you get now, rewards now, and the rewards later, the rewards later. And of course, the total is the total return. That's what these things are measuring. But by splitting it up into two parts, we can understand what it is. And that's because we know what action you pick now. So by picking your at state s and you choose action A now, the rewards it now, this does not depend on pi. So this is the whole secret, is we're kind of like peeling off the part that does not depend on pi star, which is if you're at state s and you take action A, like the policy pi star does not affect what you get now. It will affect what you get later, but it will not affect what you get now. And so what you get now will be some amount of reward, will be the r of sa, when you're at state s and you take a. So r of sa is going to be the expected reward for one step, the one-step reward starting at state S and taking action A. So that's the reward you get now. And the reward you get later, in general, that might be very complicated, but we can write it in terms of the value function v. And this was the kind of thing we saw before, is that what you got to do is you take the value function v pi star, and v pi star, that would tell you the total return starting at some state. We want to sort of shift that in time so we get the rewards later. And to shift it in time, you multiply by the matrix m. So m, I guess pi star. And then you evaluate this whole thing at the state S. And by evaluating this matrix product at state S, that's like shifting things forward in time, you get the value function not at the state S, but at one step forward in time. So maybe I'll remind you what these things are. So v pi star. Yeah, let me write down the whole thing like this. So m pi star times v pi star. At the state S, it's the expected value of the total returns one time sort of in the future. So it's the expected value. I'm going to say, I'll write it like this. R2 plus R3 plus dot, 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 given S0 equals S. And following pi star, right? Where this is in contrast to just v pi star is the total returns, but starting at the beginning, right? So R1 plus R2 plus dot, 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 given S0 equals S. So one of them is shifted forward in time, and multiplying by m exactly shifts things forward in time. I think I called this the backwards Kolmogorov equation many classes ago. Okay, and there's one other small detail you can add if you want to be a completionist, is you can put in a little gamma. So gamma, I guess these need to be added, so plus, and the gamma goes in front of everything. So this one is this plus gamma times that plus gamma times this plus dot, dot, dot. And this is R1 plus gamma times this plus gamma squared times this plus dot, dot, dot. So, okay. So there you go. Okay. And this sort of simple observation, this lets us finally solve our chicken and egg problem. And that's because v pi star is given in terms of q pi star, and q pi star is given in terms of v pi star. So if we take these two equations and we plug one of them into the other one, we'll be able to solve it. And that's exactly what we're going to do for pig in a second. But this is a great sort of conceptual place to stop and ask if you guys have any questions about what's going on. What do these symbols on the board mean? Anything? Okay, let's see it in action. And again, you can like plug this in sort of a general situation, but I think it sort of like can get quite confusing. So I think the simplest way to understand what's going on is let us think of pig. So back in pig. And that's because pig is very simple because there's only two actions. There's roll again or stay, right? So this is the example we're going to do, which is pig. And the actions are roll or stop, right? And I'm doing the one player, one round pig, right? Where you just play it for one round and you get a dollar amount equal to at the end. So the rewards are, they're not what you get on the way. It's just at the end of the game. If you choose to stop, then you'll get a reward right at the end. It's a kind of a terminal reward. Okay, so let's see what that would look like. So let's write down the first equation. And the first equation says the optimal value function, S, I guess let's write down what the states are as well. The states are going to be, I'm going to write them as 0, 1, 2, dot, dot, dot. And then I'll also, just to be super explicit, I will also keep track of like still in or not. Still alive or done. Okay, and some of them actually are super easy. Let me write it like this to make things crystal clear, or at least crystal precise. Maybe they're not clear, but they're precise. Okay, v pi star of s done. This one is very easy. If you are finished the game and you had s points at that moment, then you are finished. You get s dollars, right? So this is telling you that if you were at s points and you finished the game, then you get s. And in fact, this is true for any policy. This is not just true for the optimal policy. V pi, this is always true, right? And this is just saying that you get a terminal reward if you finish the game and you choose I'm done, then you get whatever state you're in. Fantastic. And I think I drew a little picture of this last class with this kind of thing. So you have alive or done, and if you ever choose to finish, you're at 4, and you're like, I'm going to stop, then you get $4. You move to this state, and the value is $4. So that's the value function on the done states. Questions about this one? Is the setup more or less clear? Okay. The hard part is what happens when you are not done. So you're still playing. Still playing. Okay, and again, we're interested in the optimal policy. What is it going to be? We can use equation 1 from the Bellman equation. So we can use part 1 of the Bellman equation, and it says the maximum over all the actions you can take of the two things. And in our situation, there's two things we can do. So it's going to be the maximum, and then it's going to be what happens if we roll again, and what happens if we say. Happens if we stop, comma, what happens if we roll again. So that's what's nice about this problem, is because there's only two choices, or two actions. It's pretty simple to write down. It's a maximum of two things. And one of the two things, when we stop, I already told you what it is. If you stop, then you definitely, with a 100% chance, move to the state s comma done. And if you move to the state s comma done, what will you get? Well, it will definitely be s. So the first one is s, the maximum. So the first thing is s. If you stop, it's s. And I know it's s. I guess I could write down it's a 100% chance of being v pi of s comma done, but I already told you that v pi of s comma done is s. So I'm just going to say, if you stop, you get s points. The more interesting thing is what happens if we roll again. Okay? And the problem is, again, this depends on the value function pi star. So this is technically q pi star of the state s comma still playing, when you choose to roll again. Roll again. Okay, and I guess this s was also a q function. It's what happens when you choose to stop, but that one's easy. We already know what it is. And so now the hard part is, we got v pi star in terms of q pi star. It's not helpful. But now we take our other equation, and we can say, what is the other equation? Q pi star of s still playing, and you choose to roll again. Well, in that situation, we know what happens. It's like all the things we've done in the course, where we're saying you're at some state s, you've rolled the dice again. We're going to add the dice roll on to your state s. If there's a 1 in 6 chance you roll a 1 and then you lose, but this is like all the stuff we did before. So the nice thing is, by fixing the policy pi star and saying we're going to roll again, we kind of have taken away all of the policy choices. This is just like a calculation from in the course before we knew what actions were. So got to just figure out what happens. And there's a 1 in 6 chance you lose immediately. So on average, I guess, okay, let's write down what happens. I'll do a little aside here. So what happens, there's 1 of 6 things will happen. And they all happen with probability 1/6. So you could write down the list of all the universes that happen. They each happen with probability 1/6. With probability 1/6, you roll the dice and you lose. Lose immediately. And so I would represent that by saying you go to the state 0, comma done. So you're done and you have 0 points, right? So if you're at state 1, 1/6 of the time, you will immediately lose the game, and you have 0 points. So that's one thing that could happen. Another thing that could happen, if you roll a 2, you were at s, you rolled a 2, now you're at state s plus 2. And I guess you're still playing, so s plus 2 comma still playing, if you want to be a completionist, still playing. So you're still alive, but now you're at s plus 2. You could also be at s plus 3 or s plus 4, all the way up to s plus 6. So there's sort of five ways that this can happen, still playing over here, ... Okay, so those are the 6 things that can happen to you. The Q function is the average, so you got to average these up. If you lose immediately, you get no points. So what is the Q function? Well, it's a 1/6 times 0 plus 1/6 times the next situation, and so on and so on. Now here is the thing. Normally, I'd say, okay, you're at state s+2 and you're still playing. Like, great, is that good or bad? Like, how many points do we get for being at state 2 and still playing? And just like we said before, the problem is this depends on the policy pi star. But in this situation, I have told you, we're going to follow the policy pi star. So if you're at this situation, s+2 still playing, on average, how much reward do you get? Well, it's simply v pi star of s+2, comma, still playing. Still playing. And so by kind of saying, I'm just following the policy pi star, and now I have the notation to say, look, I don't know what it is, but it is, whatever it is v pi star of s+2. And similarly, plus dot dot dot, let's do the dot dot dots down here, plus dot dot dot, plus all the way up to v pi star of s+6, comma, still playing. Still playing. Okay, and that lets us figure this thing out. Okay, and again, just like before, yeah, question?
So it's just the average of like all the possible outcomes.
It's the average of all the possible outcomes. That's right. That's exactly what it is. Yeah, and so like, I think when you write it like this, it's kind of intuitive, maybe like what happens. But what we've written is the special version of this equation, right? Which says that q pi star, it's the rewards you get now, plus the rewards later, rewrote the rewards later. The rewards you get now are nothing, right, in this situation. You can imagine a version of the game where you get like a bonus every time you roll. You get like a plus $1 bonus. Then you get a reward, you would add a plus 1. Yeah. Great. Any other questions? Okay, now that it's a little more concrete, if I said, oh no, we have such a huge problem. V pi star is the maximum of s comma q pi star, and q pi star is this thing involving v pi star. How on earth will we solve it? We say, you just take this and plug it in there. Like, just delete that, just put it, you'll be done, right? And so that's what I'm going to do. So now plug in. I'll say equation 2 into the right-hand side of equation 1. So this is like what makes the Bellman equation. The Bellman equation is that you can, even though it seems like v pi star is in terms of q pi star and q pi star is in terms of v pi star, you just plug one into the other and you have an equation in terms of itself. So all of this stuff is exactly what appears over here. And so if I plug it in, I get this nice equation. It says v pi star of s, comma, still playing, and it's just copying and pasting the maximum of s, comma, right, which is what it was over there, and all this stuff. All this stuff is quite nice. It's got a bunch of 1/6. So 1/6 of v pi star of s, comma, still playing, plus dot 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 dot, plus 1/6 v pi star of s, comma, still playing. Okay, now we have a beautiful equation. Question?
Should it be v s plus 2, dot dot dot, v s
It should be, yes. I forgot to write those. I got excited. Okay. Thank you very much. So yes, v pi star of s plus 2, comma, v pi star of s plus 6, comma. Okay. And so this is the Bellman equation for the dice game Pig. And in general, you can always do this Bellman equation, I guess for the one player, one round Pig. Okay, and it tells you v pi star in terms of itself. Okay, v pi star in terms of itself. So what kinds of things can you do if you have this equation? Well, one thing you could do is if somebody off the street comes and is like, I have the optimal strategy. I think the optimal strategy is to roll if you're at 20 or lower, and to stop rolling if you're 20 or higher, right? You could check, you could calculate, does the strategy you're thinking of, I'll calculate v pi for the strategy you're thinking of, and then I'll plug it in here and see, does the left-hand side equal the right-hand side? That's very nice. You remember last class, when we actually did this roll under 20 thing, we didn't actually prove it was the optimal strategy, right? Let's see, right? Is the optimal strategy rolling under 20? Well, we said rolling under 20 is the best of all the roll under so many strategies. but maybe there's some weird strategy that beats it. So with the Bellman equation, you can check and make sure that it really is the best strategy. But even better than that is you could just like forget about anything else and use this to find the solution. So by value iteration, I want to know what v pi star is. I'll just keep plugging it back into the equation over and over again. So can solve for v pi star. V pi star now. And the answer is by value iteration. And you'll see that all the other sort of methods in the course, all of them are different ways to solve the Bellman equation with like various amounts of limited information. In this situation, we know the Bellman equation exactly. We can solve it with value iteration. In other situations, maybe you just have like Monte Carlo samples. You solve like some like random version of the Bellman equation. We'll see that later in the course. Questions or comments about that? So that's what I'm going to really do now on the computer. I'm going to tell the computer to do this, and we're going to solve the Bellman equation. Okay, let's get some Numpy open. And so we have a new coding thing over here. And I got to do the secret buttons. This and this. Nope. That's the wrong button. This and this. Okay. All right, and we start our programs always the same way. Import NumPy as NP. Oh, okay. Well, might be a boring class if that one's not going to run. Okay, good. All right, so now we need the value function. I guess, again, as you've noticed on the homeworks, there's a problem between real life and computers, is that real life can have all sorts of interesting infinities, and computers can only have finitely many things. So the first thing we got to do is set like an S max, the maximum value we're going to look at. Let's say it's 50. And we can't look at numbers bigger than S max. We'll just say if you ever roll above S max, you move down to S max, just like you did on assignment 1. But the value function v, I'll say v still alive, and that will be a NumPy array of size S max plus 1, because we start at 0. You'll notice actually, like, I only ever need to compute what happens when you're still alive. Like, technically the other part of it is part of the game, and like it was an important part of deriving it. But like, if we can figure out what happens when you're still playing, then we will know what's up. So actually, you know what? Let me, in the interest of readability, let me just call it v, and I will leave a comment. V is the value at the state s comma still playing. So that's what I mean when I say v. The other part is trivial, so we're not going to write it down. Okay, hopefully that'll run. Okay, that's v. And now I'm going to do value iteration. And how do I do value iterations? I do some number of iterations, let's say 10, and I will do a for loop for iters in range num iters. And I'm going to type in the Bellman equation. So I set v to be the value on the other side. And the value is the maximum of s, comma, and I'm going to write these all down. V of s plus 2 plus v of s plus 3 plus v of s plus 4. Yeah, unfortunately, the computer does not accept dot, dot, dots. So you have to be a little bit more specific. Okay, because if you want, you can use a for loop. Okay, there we go. That's the Bellman equation. Yeah.
So what are the s's supposed to be, since we never define s anywhere? And also,
Yes.
Also, won't that try and access some out of bounds for some s's?
These are fantastic points. So again, first thing is, what the hell is s? And in fact, Google also agrees with you, right? What are you talking about? There's no s. I don't know what s is. And second of all, once you have figured out what s is, this is going to have an overflow. Okay, so great thing. I also left off one other thing, which is part of the equation that I didn't write. Does anyone see it? Yeah. The 1/6. Okay, yeah. Let's first mistake first. Let's do this. I always get paranoid about it changing types, so I'm always writing 0.0 for things because I'm paranoid. In all honesty, I think it would be okay. I'm sort of like, I grew up on programming languages that would just go nuts, and then you'd spend like an hour debugging it. You just have to change a 1 to a 1.0. But okay. So that's okay. So that's we got the right equation now. What is s supposed to be? Well, in our derivation, the equation has to be true for every value of s. So the equation is true for every value of s. And if you write it as a vector, you can think of it as a vector equation, where the left-hand side and the right-hand side are vectors, and every single component has to be true. So ideally, I would do it as a vector. You have a number of different choices for how to do this. One thing you could do is you could say for s in range, s max plus 1. Plus 1. And you could do this, and then it would sort of do them one at a time, and then when it's finished doing them one at a time, it would go back and do another iteration. You could also, you could say like temp. You could make a temp. So you could do that, and then you could say v equals temp. So you sort of like write them all down, and then set them to the thing. Of course, Google doesn't like me because I need to tell you what temp is. Temp is also some other vector, right? Dot zeros of s max plus 1. So this would be a perfectly valid way to do it. Write down what you want, and then set v to that vector at the end. Excuse me. Questions about this? Comments? Okay. There was the other issue, which is with the overflows. So if I run this right now, it does kind of what we want, but Google will yell at me and say, index error. Index 51 is out of bounds for axis 0 with size 51. And that's because, remember, I made s max 50, which is size 51. So 0 to 50 is size 51. And you did something at some point s was equal to 50, and then you have 50 plus 2, 52, not allowed. And we said that when that happens, we always truncate back. So I'm going to put in a little a min of this with n max, or s max. So like this. Okay, and now I got to do a lot of these. Okay. How do I make this maximally readable? I guess like this. This plus this. And I think this will run s max. You could also, I don't know, define some way of doing it. V of min of whichever is smaller. And so what this will do is it's effectively saying if you would ever roll over s max, then you just get to s max instead. S plus 5 and v of min of s max s plus 6. Okay, perfectly valid code. I hope Python likes my line splits. Let's find out. Yeah, okay, great, we did it. So that works, and that is exactly what we want using this thing. This is perfectly correct, and it's totally fine. It is slow. And the reason it's slow is because this loop is slow. So we're kind of looping a whole bunch to make the temp, and then we're just setting it at the end. Wouldn't it be nice if there was a way we could just do it in one shot and not have a temp and not have a for loop? And a big hint that you can eliminate this for loop is that what happens in one round of the for loop is unrelated to what happens in the next round of the for loop, right? When s equals 3 and when s equals 4, it's like two separate calculations. They got nothing to do with each other. And if you have a for loop and they don't depend on each other, it's a good sign that you should be able to eliminate it. And the way you can eliminate it is the hint that I sort of gave last round, which is that NumPy works perfectly fine if instead of feeding in a number, you feed in a vector. So if you just make s equal to all the indices that are over here, so if you do a range, s max plus 1, so now s is a vector, 1, 2, 3, 4, 5, 6, all the way up to s max plus 1, then this line will just run perfectly fine. So temp of s equals this stuff. It'll do exactly the same thing as the for loop. Like the code that I have now and the code that I had a second ago are exactly the same code. Yes?
You also don't need the temp anymore.
Yeah, well, okay. Well, I'll do that one in 1 second. Let me make sure this one runs. The only potential problem is that it might yell at me when I do max. Because max is a Python command, and I might need to replace it with numpy.max. So let's see. Okay, yeah, so it's like yelling at me. It's like, what the hell are you talking about? And the reason is NumPy doesn't know how to take the maximum of an array, right? Which is bigger, this array or that array. You need to do np.max. And okay, this is one of the most important bugs you need to be aware of. np.max and np.maximum are two completely different things. So you got which one do we want? One of them says you input an array, give me the largest value in the array. And one of them says give me two arrays and tell me which one is bigger. Okay, and which one is which? I always forget. What's the best way to find out which one is which? Yeah.
I think np maximum finds the largest within an array because I use np minimum in my SML reports. I think np maximum
Yes.
compares to arrays.
Yes. Okay. The way I'm going to recommend is we're gonna go ask ChatGPT. ChatGPT. Which one is np.max and which one is np.maximum? Okay. Okay, so np.max finds the maximum value in an array. So you input one array, and it finds the maximum value. Oh, there's a nice example. Very nice. np.maximum compares two arrays and tells you which one is entry-wise bigger. So which one do we want in this situation? We want np.maximum. Okay, what's this? Those are the, okay, so we want np.maximum, right? Because S is a big array, and we're comparing this array with that array over there. And then I think similarly over here we need np.minimum, minimum for all of these. Oh, and here we can do the hack that I showed you guys. np.minimum. Okay, and except for the fact that I have to do it twice now. It's all good. Okay, now it should work perfectly fine. Any questions or comments about that? I'm trying to show you guys some Numpy jujitsu over here to help you out on your coding. Okay, let's run it, and hopefully it works. Numpy has no attribute np. Yeah, np.np, not good. Okay, now it works. Okay, and now that it works, now you can see that this is very silly. I might as well delete my temp and just say v of s equals that. Okay, very nice. And the reason it's nice, right? By doing v of s instead of v, then I can index the s, right? V of s, something involving s plus 2. It's all good. Okay, and it works like that. In one line, it's a vector equation. And the reason it's a vector equation is because I fed in all the entries at the same time. Okay, great. We solved it. Okay, let's plot what we solved. How do you plot things? You do the second line of magic, matplotlib.pyplot as plot, and then we're going to plot this thing. Plot.plot. And again, I want to plot s against v of s, and let's label it iteration number whatever it is. Label equals f iteration iters. Okay, and then let me restart it at 0. Okay. Oh, actually, let me plot it before I run it, so that iteration 0 is really iteration 0. Okay. Okay. Plot.show, that'll show that I need to add the legend. Plot.legend. Okay. This should work. Fingers crossed. Okay, beautiful. So we have this beautiful plot. Now we can interpret it, and we will be happy. Okay. What is this plot saying? At iteration 0, that was in blue. We had this. We were like, all zeros. The value is 0. How many dollars are you going to get in this game? $0. Terrible guess. But that is what we told it to do, right? We said at the beginning, $0. Then, iteration 1 was orange. We took the Bellman equation. We applied it one time. And now, the guess is this straight orange line. We're guessing that you're going to get S dollars when you're in position S. Hey, that's a pretty good guess. You're going to get at least S dollars, right? Iteration 2, it went up a little bit. Actually, you'll notice it went up a little bit at the beginning. Over here, it remained unchanged, right? So if you're at like 30 or 40, that's how many dollars you're going to get. If you're at state 30 or 40, you can't improve on that. But you can improve at state 0, and that's because you can roll again, and you'll get a little bit more. After iteration 3, went up a little more. Iteration 4 went up a little more after that, and so on and so on. And in fact, why don't I have it print out what is v of 0 as we go? Print, let's see, f string v of 0 equals, and this is at iteration at iters equals, v of 0 equals this. So I get a nice little thing. Okay, so we can see the value at position 0 when you start the game with nothing is slowly marching its way up, and we can see that in the loop as well. So it starts at 0, then it's 3.33, then it's 5.55, and it gets all the way up to 8.14177, then it goes up to 8.14179. What if I run it even more times? Num iters, let's make it 15. Okay, you see it stabilizes. Eventually it is constant. It's not changing anymore. And what that is telling us is that we have reached a situation where the left-hand side equals the right-hand side. We have solved the Bellman equation. So it seems like it took 10-ish iterations here, and we have found the solution, this function on top. So it's straight for a while, and it's curvy over here. That's the solution to the Bellman equation that tells you the value of the optimal strategy in the dice game PID, and you can check that it is that roll under 20 strategy. All right, any questions or comments about what we've done? So this is great. We solved, without doing anything. We just took the equation. We did it a whole bunch of times. This is the kind of thing you're going to be doing on your homework. On your homework, the policy is given to you. There is one thing that maybe bothers you. So I solved for v, but that's not what we actually wanted. Yeah, question first.
Also, how do we know for sure that that corresponds to the role that we described?
Yes, absolutely. This is essentially the question I was just asking.
Okay.
We found v. Very nice. The value, this tells you the value, right? But what's the strategy? Like, what do I do? Right? If I want to follow the strategy that you told me, I know v. I know how much I'm supposed to get. But what do I actually do? Like, what do I do at different situations? And I made this a mathematized question for you guys. So, value to actions. Once you find v star, how do you use v star to determine which action is the best? So we found v star by value iteration, which is very nice. But that's not answering, that's the answer to a different question. How do we turn that into learning the best action? And I'll let you think for a few minutes. Feel free to discuss, and then we will take it up. All right, there's like 15 seconds left. Put in your guesses. Take any sort of guess. If you really have no idea, then put an I don't know, but the guesses are appreciated. The more creative, the better. Okay, maybe I'll regret saying that in a second. We'll find out. Okay. Okay, so we know V star. How do we use V star to find A star? That's the question. And people said, and I don't know. Iterate all A and find Q. Oh, that's a nice way to do it. That's very this would work. I wasn't gonna do it this way, but yeah. Okay, so this is the idea is, remember, if we had an equation that tells you Q in terms of V. So now we found V, you could totally take. We know V. If you know V and you know this equation that is circled in green, you can turn that into finding Q. And once you find Q, then you can figure out which one is better, right? So this is the Q rule again. I can also tell you what Q state is. Q star of S, comma, still playing, comma, stop. That is simply S. And so I can use these two equations together. I can figure out the Q value for all the V's, and I can compare them and do it. Fantastic answer. That's totally equivalent to what I was going to do. Let's see if there were any other answers. Very nice answer. Q function. Yeah, okay, maybe that's what you're thinking of. Something Kolmogorov. Yeah. Use V to solve for what? MA. We know what MA is. MA is essentially baked into this rule over here, right? So the matrix M is the matrix that has a 1/6 on like the +2 diagonal and a 1/6 on the +6 diagonal. Like the matrix M is sort of baked into this like what happens with what probability. And all of this stuff over here is really the M roll again matrix, right? Like this is representing the M roll again matrix on the vector V. So we sort of already used MA without writing it down explicitly, which is nice. Yeah, so this is what the question was. How do you do that? Okay. Find Q star. Yeah, very nice, very nice, very nice. By using Q. Okay, very nice work, everybody who said something about Q. So in fact, the way I was going to do it was totally equivalent to this. This is the two Q's. Remember though, we eliminated Q by plugging in, right? So V pi star wasn't given in terms of Q. We plugged the Q in, and we came up with this nice equation for V. V is the maximum of two things, and it's a maximum. This maximum represents the two things that can happen. So there's the roll again, and there's stop. So a stop, and all this stuff was roll again. Roll again. And V is the maximum of what you get if you stop and roll again. If you want to know the optimal action, you don't ask which one is bigger. You don't say which one is bigger. You say of these two options, which one is bigger? And that is called an argmax. So A pi star of S, still playing. Same equation, but it's the argmax. So it's the argmax. And the argmax means tell me which one. So the answer will either be stop or roll again. And again, the same two things, right? Stop and all this stuff over here. And I guess it really is Q. So maybe an easier way to say it is Q pi star of S. Still playing and roll again. So same exact answer as what people said with the Q functions, just expressed a little bit differently. Maybe your way of thinking about it is actually clear. Okay, so roll again. So here we go. Roll again. So the value function is the value of whichever is bigger, and the optimal action is which of these two options is bigger, and that'll tell you exactly what's happening at state S. I saw a question over here, maybe? No? Okay. So now we're just going to ask the computer, don't just find the maximum, find the argmaximum. Tell me which one is bigger. There's a number of ways you could do it. You could put this in an array. You can make this index 0 and index 1. In this particular case, because there's a nice formula for S, what I could do is I could just look at the difference. Look at V pi star of S. Oh. Let me pause here to fix a tech issue. Okay, V pi star of S minus S, and that will be the maximum of 0 and this stuff. Let's say V pi star of S plus 2 minus S. And what will happen is when this number is positive, then you should roll again. When this number is 0, you stop. If this is a negative number, then that means that rolling again is better. So actually, this is all totally equivalent to, let's say it this way. Yeah, let's do it your way. Let's calculate both Q's. Okay. All right, let's just do it in the code. I think I'm sort of belaboring an easy idea over here. So let's do it in the code. Okay, so here we go. These were the V's. Let's calculate the Q's. So let's call this Q stop. That's easy. That's S. Remember, S is our little array over here that lets us do everything. And I want it to be like this. So that'll be stopping. And I got to tell the computer what is Q stop. Q stop. Yep. And then I got to make a Q roll again. Q roll again. And that will again be started out as all zeros. And then I will set it to this thing over here. So Q roll again is equal to this. That is what the equations say. Okay, there we go. So I made the stopping, I made the rolling again, and now we should be able to compare them. Why don't I just put this in a separate block here? Okay, and now we can compare Q stop. Let's make the first 20 entries. So you can go 0 to 21. That'll say, please output the first 20 entries. And Q roll again. Roll again. 0 to 21. So this is saying if you choose to stop and you're at state 3, you get $3. If you're at state 3 and you choose to roll again, you actually get $8.5. So it's better to roll again than to stop. So you want to know what's the optimal action, you can write down when is Q roll again greater than Q stop. And this will be an array of ones and zeros. And it'll say, look, it's better to roll again here. It's better to roll again there. True, 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 true. All the way up to line 20, it is not better to roll again than to stop in position 20. And that's because they're equal. They're both 20. You could go up even further. Let's go up to the first 30. And 30. And now you see that if you stop, and if you have 28 points and you stop, you get 28 points. But if you're at 28 points and you choose to roll again, well, then you're a dummy because you only on average get 25.8 points. And now we can see which one is bigger. And again, you get trues and falses, and they indeed do stop exactly at 20. So all of these points, it really is this part of the curve. So on this part of the curve, the maximum is stopping, and on this part of the curve, the maximum is rolling again. Okay, fantastic. We've solved the dice game Pig beyond any reasonable amount. Questions or comments? Okay, let's do one more fun little variant, which I have in Mathematize. Here's a new version of Pig. There's an extra rule. If you get to 40 or higher, you get a 5-point bonus. So you're at 39, you roll again, you make it to 41, then I'm going to give you an extra $5 at the end of the game. An extra $5. How would you put this into our solution? So I'll let you guys think. Type in your answer here. What would you modify? And then it should be a pretty quick modification in our code to see what to do in that situation. The other fun thing, if you think this is an easy problem, you know exactly what to do, try to ask yourself, what is the optimal strategy going to be now? So before it was roll at 20 or below and stop above. What's the strategy going to be now? Do you have a question or a comment? Or?
Do you have to bank to get that 5, or you just get it?
Oh, no, you have to bank. Yes.
So when you get to 40, you just instantly go to 45.
Yeah, you can think about it like that. But also, if you get to 42, you instantly go to 47 and so on. So like, you can think about it like that. Yeah. Yes, great. Fantastic question. Yeah, so Q roll again. It was a copy paste of all the stuff that went into the second maximum. Yeah, so it was all the stuff over here that went into the second, the maximum. Yeah. Yeah, in fact, now that I've written the whole thing, it would have been nicer to write Q roll again and Q stop here, and then I could have written the equation that V of S is the maximum of the two Qs. That would have been a nicer way to write it. Okay. Okay, let me give you 1 minute to tell me how you would modify what we did. Okay, 10 seconds left. Put in your guesses or how you're thinking about this. I think there's more than one way to do this. Okay. Let's take a look. What did people say? Oh, haha, oh, little donut. This is amazing. It says I don't know. Okay, very, very clever. Okay. All right, let's see. So there's one kind of very like pedestrian way to do this, which is you could just say like you change the matrix M, like you change the probabilities. You say instead of doing an S plus 2, you like add 5 to it, right? So instead of going from 39 to 41, you go from 39 to 46. I wonder if anybody wrote that. That's sort of the sort of easy way to do it. Yeah, so the transition matrix, I guess that's what it is. Did anybody write this? Yeah, new state space, the transition matrix. So that is like how you could think about it. You're like, this is a whole new game. It's like a whole different snakes and ladders board, and there's different snakes and ladders on it. But there is also a way you can do it by just modifying some of these things that we already have. And that's what some other people wrote. So, yes, okay, let me stop the timer. Okay, into QPy of still playing roll again, if s greater than 0, update s to s plus 5. So what you want to do is change the value of the Q function. I think not this person maybe didn't mean for, because roll again, it's like some weird combination, but for stop, that will be s plus 5. So that's very close to the right answer. Let's see if anybody did it. Yeah, okay, this is it. So add a terminal reward where if s is bigger than 40 and you're done, it becomes s plus 5. So this is the right kind of way to think about it. And in our code, it's actually very easy to write. So I'm going to copy and paste these Qs, which we did later. Let me put them in up here. And actually, what we did with V was the maximum of the two things. It was the maximum of Q roll again of S and Q stop. Oh, I need Q stop. What do I copy paste? Okay, I gotta get this one. Q stop. Q stop. Let me do them in order. So Q stop is first. Q stop of S and Q roll again of S. Okay, and this one you don't even need to write S, but let's just write the S in. So this is exactly what we had before. And to change it, you just got to change what happens in this Q stop. So this is kind of like the like anchored final value, and I can just change it to add on 5 points if S is bigger than 40. And one way to do that in Python, you just say S is bigger than 40. That will, I guess it's greater than or equal to 40. That will be a number, either 1 or 0. So that's 0 if this is false, and it's 1 if it's true. If I multiply it by 5, that'll add 5 points. So by adding on 5 points to Q stop, and then just doing the equation, everything will work just fine. You'll notice actually that this one gets updated. So every iteration, this one's getting updated by the V's. This one's always a constant. I could have taken this out, but that should work. Questions before I run it? Yeah.
So does Python generate just read Boolean values of 0 and 1 always?
Yeah. If you try to multiply a Boolean by like 5, it'll turn it into 1 and 0. So I think what'll happen under the hood is it'll first make 0 greater than or equal to 40 as trues and falses. And then if you ever do anything with it that's like numbery, it'll convert it to 1 and 0 like on the spot. Yeah. So yeah, this should work just fine. If you want to be extra careful, put 5.0. Okay, let's run it and see. And we have this nice plot. Okay, and the legend is getting in my way. Let's make the legend go away. So what's happening is, at iteration 0, we get 0. After one iteration, we got this thing with a kink in it, because we're getting plus 5 points exactly at 40. And then over many iterations, we converge to the right answer. We get closer and closer to the right answer. Down here, it looks exactly the same as before, but now we have this new little spot over here where you're slightly beating out that thing. And if we now compare, where is it that Q roll again is bigger than Q stop? Actually, why don't we compare the values? And I guess I got to do, let's say, up to 50. Okay, so over here, you can see these are, if you stop, it goes from 39 to 45 because of that plus 5 bonus. And over here, you can see some funny stuff. It's very complicated, but if you say, where is it larger, then you get some interesting things. You got to go up to 50, though. You'll see that it's true, 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 true. So for a while, you want to stop, and then you want to stop in here in the middle, but then there's a couple trues over here. Why don't we have it output the indices where this is? How would I do that? Oh, yeah, there's a command called where, np.where. Where is this bigger than that? And it should output the numbers. Okay, so you roll again on 0 to 19. You stop at 20 to 35, but 36, 37, 38, and 39, you want to roll again. And that's because now there's a bonus, so it changes the optimal strategy. The optimal strategy is no longer stop below a certain number. This little plus 5 bonus made a little island of numbers where if you get there, then you want to keep going. Yeah?
At that point, would it be your choice to roll to go higher now?
You mean like 40?
Like if you're between 20 and 35.
No, you should stop. Yeah.
How do you?
You're pointing out that the professor is a very bad game designer and designed a game where something interesting happens at 36, but you never get to 36. Well, little do you know, there's 4 more questions where we add more rules that no, I don't know. Yes, this is a good point. You would, even though if you're at 36, you should roll again. If you follow the optimal strategy, the highest you will ever get is 26. So it's true that perhaps I made a little silliness, but yeah. The point is, I guess the thing I wanted to show you is that with this method, you can put in any rules, and you don't need to do some like bespoke like hand calculation to figure out what is the optimal strategy. You throw it in the value iteration, and it will figure it out. And it works even if the policy is some weird thing that is like sometimes do this, sometimes do that. In this weird situation, do this. Like it'll figure it out. Okay. Was there another question here? No. Okay.
Will this be posted online?
Yes, I can post these online, and also the video recording will be up. So yeah. All right. What is next? I want to get to the 2-player version of Pig. So far we've done 1 round, 1-player version of Pig. We're very close to being able to do the 2-player version of Pig, but I'm going to do a little in between as like a little thing halfway between where we are now, which is 1-player, 1-round Pig, and 2-player Pig, which is we're going to need 1-player multi-round Pig. And in this version, you get, instead of saying you get $1 per point, I'm going to say you win if you get above 50, and you lose if you don't get above 50, and you have 5 rounds to try to get to 50. So if it was try to get to 50 in 1 round, that would be very boring. Like you roll again if you're below 50, and you stop if you're at 50, right? Like there's nothing to do. But in 5 rounds, then it's like strategy. It's like how aggressive should I be? If I get 20 in my first round, is that good enough? Or like can I stop at 10? And this will fit our framework, but we have to change some things. And so I want you guys to think of what is going to have to change to solve this new problem. So this is like 1-player multi-round Pig. What do we have to change? What's going to be the new problem? Okay, I'll give you a minute to do this, and then we'll take it up, and I will tell you the answers. Okay. All right, 10 seconds left. Put in your guesses. Which things are going to change? Okay, let's take a look. What will change? All right, the rewards, the states, the actions, the probabilities. People are on the right track here, which is you're going to have to change the rewards and the states. The actions are still either roll again or don't, but what those actions do will be different, right? So like where they take you, and that's because the states are going to be different. So like instead of pointing to a certain thing, it'll point to something else. The probabilities will still be 1/6 for certain things and 1/6 for other things. So that's what's going to happen. The main thing that I think some people find hard to figure out is what should the reward be in this game? So let's try to quickly brainstorm here. What should the rewards and states be in 1-player multi-round Pig? And this will sort of warm us up for the 2-player version, which we're going to do in a second. Multi-round Pig. Okay, states and rewards, those will be different. Okay, someone want to take a stab? What are the states or the rewards? What should they be in this version? Yeah.
There's 2 scores now,
Right. Okay.
so you have to have 2 lists.
So the state is no longer 1 number, it's 2 numbers. So the state is 2 numbers. Let's say it's let's call it the amount you have banked already. we can call that B for banked, comma, and then we can call it like current amount. We'll call that C, right? And so there's two numbers, because maybe you've already banked 20, and then you're in this particular round you're at 10. So like you got to keep track of those two things separately, because if you lose the game, you don't lose the B, you only lose the C. So that's important. Two numbers. Great. Anyone have anything to add? Yeah.
Whether we're still rolling or whether we decide to pull it in for at least one of the rounds, in the 5 rounds, in the 5 never mind.
I don't know. I'm trying to understand. I think what you're saying is the actions are different, right? Is that what you're saying, or the? Yeah. Okay. This is true. I guess technically you should add like times still rolling, as you saw kind of before. If you kind of think about things the right way, and you kind of think of the stopping as like a terminal state, then you can sort of pretend that everything is still rolling, still playing. So let's say this is still rolling. If you want, we can add a special state over here that's like the done state. We can add that as well. Yeah. The number of rounds that you played. Where would that go?
That's the state.
That's also part of the state. So you thought there should be 2 numbers in the state. You think there should be 3 numbers in the state? Is that right?
Or at least one more.
At least 3. Okay, very good. Yeah, good way to cover yourself. Yeah, 3. So there's also T. You could do the number of rounds you've done so far. I like to do the number of rounds remaining. So I'm going to do the number of rounds remaining. And that way, when T equals 0, that's like the end of the game. So the T equals 0 is the we know what happens at T equals 0, which is how I think about things. I said 5, but it's going to turn out that you can, with the same equation, you can do any number of rounds. You just start at a higher value. Anyway, so that's very good. Anybody think we're missing one? So far we got 3 numbers now. It went from 1 number to 3 just by doing this multi-round thing. It got a lot more complicated. Okay, anybody have any ideas for the rewards? What are the rewards in this case? Remember, this time we're not getting 1 point per thing you've banked. We're trying to get to a goal. I think I said 50. Yeah.
Is it the number of points you have or 0 if you get to the 5 rounds? I don't know.
Okay. Yes, this is very good. I think you're thinking along the right lines. I'll tell you guys what this one is. Okay, I'll just tell you now. Okay, so what is this one? This one will be, and again, it's a kind of a terminal reward only. Terminal only. So there's no ongoing rewards. And the terminal rewards tell you what is the value of any situation. If you've banked C and you have a current amount, if you've banked B and you have a current amount C, and you're at time 0, so there's 0 rounds left, this will be some fixed value. So this is a little bit like in our last one. We said, if you stop, then I tell you, I know it's for sure it's S, and we sort of use that as part of our solution, right? In this one, we know what happens at time t equals 0. So there's kind of a base value. What should I write over here? Does anyone know what you would write? Yeah.
Would it be like 0 if your score is below 50 and you some other value for the reward if you're above 50?
Yes. Yeah, that's great. And the other value, normally people use the value 1. So you're like, you get 1 point. And the problem is, you got B and C. So which one? So when you say the value, yeah.
I think it depends on what you're defining C as.
Uh-huh.
Like if C is just the number you've gotten in the current round,
Yeah.
then it'd be B plus C.
Yeah.
Or if like C is the cumulative amount.
Yeah, okay, this is great. I'm thinking of C as the amount in the current round only.
Okay, then I would say B plus C.
That's what I would say that as well. Great. So it's this if B plus C is greater than or equal to 50, and it's 0 otherwise. So we sort of have this initial, this initial value, this like terminal value that is anchoring. We know for sure this what happens, and this happens for any policy pi. So no matter what you do, for any policy pi, and then the optimal strategy is going to somehow depend on this thing as an initial value. It is very similar to in the one we did before with S. So, and by making it 0 or 1, the v's are always expected values. But if you have the expected value of something with a 0 and something with a 1, the v's will be the probabilities, right, of winning. So if we set it up like this, v of BCT is going to tell us the probability of winning when we have banked B already, our current amount is C, and there's T rounds remaining. So that's what we're going to do. In the last 1 minute, this was just a warm-up to get to the 2-player version of Pig. And so I'm going to ask you guys, before you go, the 2-player version of Pig, skip that thing for now. How many entries are there? So in the multi-round 1-player version, there were 3 B, C, T. In the 2-player version, how many states should there be? So is it a pair of numbers, a single number, a triple, or a quadruple in this case? So we'll do this as the last question today. And then next class, we will finally solve 2-player Pig. I will say, if you want like a spoiler, you can go to the video and sort of watch the last 10 minutes of the video. And there's also a nice paper that we're going to read on 2-player Pig. Okay, so do this in the last 30 seconds here, and then we will call it a day. Any questions or comments before we go? Okay, 15 seconds left to put in your guess. In the 2-player version of Pig, first to 100 points. Is it 1 number, 2 numbers, 3 numbers, or 4 numbers? Okay. What did people say? People said a quadruple. That's the wrong answer. Okay, we'll take it up next class, and we'll see that it's not a quadruple. Okay, so try to think of what it is. All right. See you guys on Thursday.